The magnetic compass is an ancient instrument. Now, although its origin is unknown, the earliest compass seems to have consisted of a magnetized piece of metal resting on slivers of straw that floated in water. Now, this was about 1,000 years ago, and it was believed at that time that the needle of such a compass was attracted by Polaris, the North Star. Now, the compass card, just so happens I happen to have one, upon which is printed a compass rose, appears to have been developed by Flavio Gioia, an Italian who attached the card to a piece of lodestone in the 14th century. Christopher Columbus reportedly used a compass that consisted of a single needle supporting a paper compass rose that pivoted on a steel point. Now, the modern compass consists of two parallel steel bar magnets that are mounted on a float and surrounded by a compass card or indicator that hangs like a pendulum and behaves like a plumb bob. Now, this is one reason that the compass card tilts inside the instrument case during changes in aircraft attitude. The instrument is filled with a liquid to dampen compass oscillations. Now, the liquid also provides buoyancy to reduce internal friction and lubrication for the bearings. Now, years ago, compasses were filled with alcohol, which explains why they were called whiskey compasses. But modern compasses, like this one, are filled with kerosene and are called wet compasses. Now, aircraft compasses are less accurate than those used on ships. That's because they're smaller and lighter. They're also subject to more vibration, acceleration, and shock. Yet they're so reliable that pilots take them for granted. We make it a point to check virtually everything on the instrument panel. The gyroscopic heading indicator is set to match the compass heading, but that is usually the extent of our apparent interest in this instrument. But we really can't afford to be so complacent about the compass because it can contain serious errors that could lead us astray. Now, assuming that a magnetic compass is in good condition, errors in level flight are caused by magnetic deviation. Now, this is a localized magnetic field in an aircraft that attracts the needle in the compass and causes it to deviate from the proper magnetic heading. It is the result of aircraft parts that have become magnetized, electrical wiring and current flow, and the operation of magnetos and alternators, or generators. Deviation, of course, does not have a fixed value and varies with the magnetic heading of the aircraft. The FAA requires an airplane to have a deviation card that displays the amount of deviation in heading increments of no more than 30 degrees. Such deviation must be determined with the compass in level flight attitude and with the engine running. The radios may be on or off. Now, more than 10 degrees is allowed, but only if the deviation is known to be caused by a specific piece of equipment. For example, turning on the windshield heat of a Piper Cheyenne 1 causes a deviation error of as much as 25 degrees. An airplane's first compass deviation card is prepared by the airframe manufacturer, but it's only accurate at that time. Now, this is because the causes of deviation change as the aircraft and compass become older. Deviation also changes with the addition, removal, and exchange of electrical equipment and avionics, and yet no one bothers to prepare a new deviation card. As a result, compasses are typically out of adjustment and placarded with deviation cards that bear no similarity to reality. Now, during an inspection of 43 randomly selected aircraft here at Santa Monica Airport in Southern California, 40 were found to have deviation cards that were prepared when the aircraft were new. Now, 14 of these aircraft were more than 20 years old, and 6 of the aircraft had no cards at all. If this is representative of the general aviation fleet, then most of us have no idea how much in error our compasses might be. Now, there's a simple way to check compass accuracy at least once during every flight. Simply line up with the runway and add some power with the brakes locked. Now, this ensures that the alternator or generator is charging and producing its normal effect. Then, note the compass heading. By doing this on a number of different runways, A new compass deviation card can be constructed with, well, very little fuss and bother. But it's important to consider that the exact magnetic direction of a runway cannot be determined simply by adding a 0 to the runway number. Now, runway 11 at Tucson, Arizona, for example, has a magnetic direction of 123 degrees, not 110. Now, the exact direction of a runway can be obtained from an instrument approach plate or from a tower controller. The most accurate way to determine all of the deviation errors at one time involves a procedure called swinging the compass. Now, this consists of turning the airplane to various magnetic headings, usually in 30-degree increments, and noting the compass headings. The difference between each compass heading and its related magnetic heading, of course, is the deviation. A compass swing can be accomplished on the ground or in the air. Now, when done properly, the air swing has the potential to be the most accurate because the aircraft can be placed in a level attitude with the engine developing cruise power with the landing gear retracted. I'll bet you didn't know that gear position can affect compass deviation. Well, it can. A ground swing, however, is usually sufficient for most purposes. It is also simpler and less expensive. And an aircraft on the ground can be held rock steady on a given heading so that the compass will read more accurately. A ground swing often is performed using a compass rose painted on the ground. But many airports don't have a compass rose. And when one is available, the job often requires two people because someone usually must be positioned outside the aircraft to help the pilot precisely align the aircraft in the proper directions. But there is a more convenient way to ground swing a compass, a method that requires neither a compass rose nor an assistant. All that is required is a reliable gyroscopic heading indicator, a directional gyro. Now, the first step requires that we obtain the precise magnetic direction of any runway associated with a long parallel taxiway. Well, now here at Santa Monica, we have no choice. There's only one runway, and its bearing is 211 degrees. We then taxi the aircraft onto and exactly parallel with the stripe. Now, this is the stripe on the taxiway, not the one on the runway. This is relatively easy, as long as the stripe is at least 100 yards long. Now, be certain that the aircraft is not near any magnetic disturbances, such as electronic generators, large motors, iron cables, and so forth.
And be sure that all extraneous tools and equipment have been removed from the cockpit. Now, as you can see, a nearby metal object can have a significant effect on compass accuracy. Also, turn on all electrical equipment, including radios that would be used in normal cruise. Now, the next step involves setting the heading indicator to the exact magnetic direction of the runway, which in this case is 211 degrees. Then turn the aircraft left or right to the first 30-degree heading increment, which in this case is 240 degrees. Now, with the aircraft aligned on this heading, note and record the compass heading. Then, we simply continue turning the aircraft in 30-degree increments while recording the compass heading at each stop along the way. Now, when the aircraft has turned 180 degrees, realign it with the taxiway stripe while heading in the direction opposite the one used initially. The purpose of this is to make sure that the directional gyro is not precessed while the aircraft was being maneuvered. Now, precession can be avoided by making taxiing turns slowly, not jerking the aircraft with the brakes, and accomplishing 180 degrees worth of ground swinging in minimal time, about 2 or 3 minutes. Complete the swing by continuing the taxiing turns until compass headings have been recorded for all 12 30-degree increments. Now, after the aircraft has completed a full circle, check the heading indicator once again for precession. By the way, a normal gyroscopic heading indicator precesses about 3 degrees every 15 minutes. More than 4 degrees in 10 minutes might indicate a gyro malfunction. Now, if desired, a second ground swing can be performed with the radios off. After all, a reliable compass takes on even greater significance in case of avionics failure. Now, the final step simply involves entering the results of the swing on a compass deviation card, which you can obtain from any instrument shop. Now, you might also want to plot the deviation on a graph like this. The deviation shown on this graph is acceptable because it does not exceed 10 degrees on any heading. Note also that the total amount of positive deviation is equal to the amount of negative deviation.
But if the deviation on any heading exceeds 10 degrees, or if there's considerably more deviation in one direction than in the other, you should have the compass adjusted by a certified repairman so that it will read more accurately. The magnetic compass contains two small compensating magnets that are used to counteract the local magnetic fields in the aircraft that affect the compass. The process of adjusting these magnets so as to reduce deviation to acceptable levels is called compass compensation. Now, the only tool required is a small screwdriver made of a non-magnetic material like brass, plastic, or aluminum. As when swinging, the aircraft is aligned in various magnetic directions, but instead of simply recording compass headings, as when swinging, the instrument technician first removes the small rectangular plate on the face of the compass. Now, this will expose two screws. One is labeled north-south and the other east-west. Now, notice the effect that adjusting a compensating magnet has on the compass card. Once a compass has been swung, or compensated and swung, turn various pieces of equipment in the aircraft on and off to see if any of it has any effect on the compass. Moving the control wheel fore and aft on some Cessna 172s, for example, can produce as much as 15 degrees of compass movement. Also, be on the alert for compass problems, such as a sticking compass card or one that touches the glass face of the instrument. A vibrating compass card could be caused by an internal problem, but often is eliminated by changing propeller RPM just a little bit. A low fluid level is not a serious problem, but the compass should be refilled by a repairman. Bubbles in the fluid? Well, this might indicate that the fluid is swirling and can result in an incorrect heading indication. The ancient magnetic compass may not be very exotic or exciting, but it is one of the most necessary and reliable instruments we have. It does, however, require care and attention that it all too often fails to receive.